Well, hi there. Today we're going to be talking about analyzing functions using their derivatives, with a special focus today on polynomials. To be successful at this task, we need to understand a few very key relationships between the derivative and the original function, as well as the second derivative in the original function. Maybe most important here, we understand that the first derivative allows us to determine where a function is increasing and decreasing and the locations of any local extremes. If the derivative is positive, this means that the original function is increasing. If the derivative is negative, then we understand that the original function is decreasing. And if the derivative changes its sign, this means that we have some kind of local max or min. If we go from positive to negative, then the original function has a max, and if we go from negative to positive, then the original function has a min. Now, the relationship between the second derivative and the original function is a little less consequential, but still important nonetheless. See, if the second derivative is positive, this means that the original function is concave up, whereas if it's negative, this means that the original function is concave down. And in the event that your second derivative is equal to 0, we call this value a point of inflection. Clearly, there's a lot of information that we can glean from these two derivatives here. If we're ever trying to analyze a function, then usually the best avenue that we can take is find the two derivatives, set them each equal to 0, and solve, and then use this knowledge here to help us figure out what's going on, over which intervals, and at which points. Let's take a look at this example problem as we analyze it till the cows come home. So the function we're dealing with here is f of x equals 3x cubed plus 3x squared minus 8x plus 7. And we are asked to find a whole lot of information here, folks. We want critical values, intervals over which the function increases and decreases, the locations of any local max or min values, the locations of any points of inflection, and the intervals over which the function is concave up or down. Sounds like a lot of work, but most of it comes down to doing two things: finding the first derivative, setting it equal to 0, and solving, and finding the second derivative, setting it equal to 0, and solving. So why don't we just go ahead and jump into it, and then we're going to refer to the notes above to try and figure out how we can specify this information. So here goes nothing. To get f prime, we're going to take the derivative of each individual element of f of x. The derivative of 3x cubed is 9x squared. Of 3x squared is 6x, of negative 8x is negative 8, and then the derivative of 7 is just 0, so we're not even going to write it. We do the same thing for f double prime, but with f of x instead. The derivative of 9x squared is 18x, and the derivative of 6x is 6. We're not even going to bother with the negative 8 there, because we understand that the derivative of a constant is 0, and it's not even worth writing down. For our analysis, let's start by taking f prime, setting it equal to 0, and solving. This will get us our critical values, which will enable us to get all kinds of other information. So we take f prime, set it equal to 0, and that gives us 0 equals 9x squared plus 6x minus 8. We can factor this. You'll have to take my word for it, but we get 3x plus 4, and then 3x minus 2. Let's forego the usual process of solving for now. We want to save a little bit of time and get to the actual calculus. I trust that you would be able to figure out that x is equal to negative 4/3 and x is equal to positive 2/3. And hey, but what have we found but two of the several pieces of information that we're asked to find up above? These are our critical values, where the derivative is equal to 0. With this, we can figure out where the function increases and decreases and where we have maxes and mins. We're going to set up a number line and call it sines of f prime. We'll put our two critical values on it, and then we'll figure out whether or not the derivative is positive or negative to the left, between, and to the right of these values. We'll start with the left-hand side. Pick a value that's less than negative 4/3 and plug it into the simplified f prime so that we can figure out whether the derivative is positive or negative to the left of that value. Remember, your specific answer is less important than whether or not it's positive or negative. So if we plug in something like negative 2, we're going to get negative 6 plus 4 in the left parentheses, and that's a negative. And then we're going to get negative 6 minus 2 in the right parentheses, and that's also negative. Negative times negative gives us a positive value. Alright, 1 out of 3 done. Let's plug in something between the two things. We'll plug in 0, we get positive 4 and negative 2. Positive times negative is negative, and then to the right we'll plug in 2, and we're going to get positive times positive is positive. Again, you may have to take my word for it, but at least you know how to do it. Now that we have this information, we can see that f of x increases over the intervals from negative infinity to negative 4/3 and 2/3 and on. We know this because the derivative is positive over those intervals. We could write this in interval notation as negative infinity to negative 4/3 open, union 2/3 open to infinity. Infinities always get open parentheses, and so do critical values because the derivative is 0 at those values. F prime is negative here from negative 4/3 to 2/3, so f decreases over the interval from negative 4/3 to 2/3. And this, ladies and gentlemen, is another piece of information that we were asked to find from the beginning of the problem. The first derivative tells us one more thing. See the sign changes at x equals negative 4/3 and x is equal to 2/3? These are locations of local extremes. Since we go from positive to negative at negative 4/3, this means we have a local max at negative 4/3, comma, whatever we get when we plug in negative 4/3 to the original function. Once again, let's save a little bit of time by foregoing the calculations, and you can take my word for it. When you plug in negative 4/3 to the original function, you're going to get the value 1/43/9. So this is where our local maximum is. Since we go from negative to positive at 2/3, this means that we have a minimum value at 2/3, and again, whatever we get when we plug in 2/3 to the original function. And this ends up being, drumroll please, 35 out of 9. So we have our two local extremes. Well, we have officially exhausted all the information we can get from the first derivative, so let's turn our attention to f double prime. Like before, we start by setting it equal to 0 and solving. If we go through the normal solving procedures, this is going to give us an x value of negative 1/3. To figure out our concavity, we're going to construct a very similar number line here, but instead of signs of f prime, we're going to call this signs of f double prime. And we're going to take this 0 value that we found, and we're going to put it on the number line. Pick a point to the left and plug it into 18x plus 6. Let's say negative 2. We can clearly see that that's going to come out to a negative value, but you can check if you want. Pick a point to the right. How about 0? 0 plus 6 is positive. Okay, so what does this tell us? Well, remember, the second derivative is all about the concavity. We know that our function is concave up, wherever the second derivative is positive, so from negative 1/3 to infinity. And we can write that interval like this. Same as before, we're going to leave that open at negative 1/3 because it's equal to 0. Means it's neither positive nor negative. We can tell that we're concave down when the second derivative is negative, like we see over this interval from negative infinity to negative 1/3. So we get this piece of information right here. And this is where our function is concave up and concave down. We've got one more thing that we got to look for. So points of inflection are going to occur where the second derivative is equal to 0. So we're going to say our point of inflection, like that right there, is located at our negative 1/3, and then to figure out the exact point once more, we're going to have to plug this value into the original function. But I did all that work for you. This is going to be negative 1/3, comma, 89/9. And wow, hey, we found everything that this question was asking us to find. That's pretty crazy right there. And all of that from just finding two derivatives. Well, I mean, obviously we had a lot more work to do, but what was that work? It was find the derivative, set it equal to 0, and solve. That's basically what it always comes down to. When in doubt in calculus class, set the derivative equal to 0 and solve. It also pays to know where these derivatives are positive and negative. To figure that out, the best thing you could do for yourself is to set up these number lines, call them signs of f prime or f double prime, and then pick values to the left, between, and to the right of these clearly important values, plug them into your simplified derivative, and then figure out if your answer is going to be positive or negative. No need to get more complicated than that. You will get confused. Remember, find the derivative, set it equal to 0, and solve. Find the derivative, set it equal to 0, and solve. You are brainwashed now.